So thanks to the organizers first for this invitation to this fantastic conference. It's a pleasure to be here. And indeed, I'm going to talk about vanishing corrections for the position of a linear KPP front. And this is a joint work with Eric Brunet, Simon Harris, and Matt Roberts. Okay, and I'm going to spend some time reviewing classical results about KPP equations. So apologies if this is stuff you already know very well, but I figured it could be useful for some. So what's the FKPP or the KPP equation? So KPP is for Kolmogorov-Petrovsky and Piscounof. Well, it's an equation which was introduced in 1937, actually in two papers simultaneously, on one hand by Fisher and on the other by Kolmogorov-Petrovsky and Piscounof. And it's a partial differential equation for a function u of x, which is going to be in the real line and time t positive, and which is like this. So you say that dtu, the derivative in u, is the sum of the Laplacian, essentially, plus u1 minus u. And this is, of course, a diffusion operator, and this is called the reaction operator. I'm going to explain this terminology in a minute. And more generally, of course, you could do this equation on dimension greater than 1 on Rd. In that case, you just put really the Laplacian here. Okay? And why is it called a reaction diffusion? Well, if you think, for instance, about a chemical reaction in which you have two species, A and B, and they react in this way. So one molecule of A combined with one molecule of B to give two A's. And you start with one, so my A molecules are green here. So they live in some medium and they move around. And when they meet, they do this, they perform this reaction, okay? And so what you're going to have, of course, if you wait a little bit, is you're going to see this cloud of green particle which is going to start to invade the whole plane, right? And if you do this in the limit and you take a scaling limit, if you do this in the limit of infinite densities, essentially the shape of the green, the density, of the green particles is going to satisfy such an equation. So that's why it's called a reaction diffusion equation. And of course, this applies to a chemical reaction, but you can also think of situations in ecology, which involve things like that, where the green particles are an invasive species which is invading some biotop, for instance. Or you can think, and in fact this was, so those ecological and biological applications were actually the original motivations of Fisher and KPP, in fact. You can think of this as a mutant allele which is invading, which has some fitness advantage and which is invading population. Okay, so what can we say about this equation? Well, the first thing you can say, which is very simple, is that of course you have two trivial solutions. So the one which is always 0 and the one which is always 1. And of course, the one which is always 0, you're going to call unstable. And this is because if you start with a small perturbation, okay, so you're considering solutions which move between 0 and 1, and your initial solution is almost always 0 except at a small place. Okay, this little bump of mass here is going to start to grow and invade everything. And conversely, if you start from almost everywhere 1, except somewhere where you're missing a little bit of mass, this is very quickly going to be erased and you're going to go back to 1, right? So 1 is, and this is because, of course, this u1 minus u here is positive, so it's a growth term. Okay? So 1 is stable. Okay? So maybe the first very interesting thing you can say about this is that this solution is going to have a traveling wave solution. So what is a traveling wave solution? It's a solution of the form u of x and t is simply some function w of x minus ct. So what this means is that the solution to the equation is a constant shape here, w, which is moving to the right at speed c, okay, velocity c. And if you're going to be a solution of this type with velocity c, you can just plug this back in your original PDE, and what you get is an ordinary differential equation for w, which is this guy. And so the question is, okay, if I give you a speed c, is it clear that you have a solution to this ODE? Okay, if you have such a solution, then this guy is going to be indeed a traveling wave solution. And the answer is in the 1937 paper by Kolmogorov et al. And it is that you have indeed solutions. So I'm going to look at solutions that goes from 1 to 0 because I want to see situation in which the stable phase is invading the unstable phase. Okay. So I'm looking at solution which goes from 1 to 0. So 1 at minus infinity, 0 at plus infinity. And you're going to have such a traveling wave if and only if the velocity is bigger or equal to 2. Okay? And of course, if I give you one traveling wave, and then I take a shift of this traveling wave, it's still a solution, right? If w of x minus ct is a solution, then so is w of x minus ct plus k. But up to this horizontal shift, you have unicity of the traveling wave solution. There is only one. All right, and so if I were to take a solution that goes from 0 to 1, then I will have the same solution, but they will go in the reverse direction. They will go with a negative speed. They will go to the left, because 1 is always invading 0. Okay, so that's very good. You have existence of traveling wave solution, but what happens if you don't start from one of those traveling wave shape, right? So suppose you start from the Heaviside initial condition, from this step initial condition. So you're 1 to the left of 0 and you're 0 after. Okay, so if you're good, you can do numerical simulations, and I'm not, so I'm going to do numerical simulation by hand. So you wait a little bit, and what you see is that there is this shape which starts to emerge and which is at the same time moving to the right. Okay, so you trust me on my word here. And this shape, if you do the simulation, actually, you see that it really looks like it's a constant shape, and the speed looks like it's going to be 2. And in fact, this is the case, and it's also back in this original seminal paper of 1937, that there exists some centering term, MT, such that if you look at your solution, so started from this special Heaviside initial condition, okay, and you look around this magic position MT, okay, what you see is that you're converging to a limit shape, okay, which I'm going to call W star of x. And this centering term is MT equal 2t plus some smaller order correction. So W star of x is actually the traveling wave solution with speed 2. So it's a critical one, so it's the slowest one. Okay? And that was that for a long time actually, but you may wonder, okay, what is this small o of t here? So first of all, I think this is a particularly striking result. I mean, it's very interesting. I'm going to tell you what it means probabilistically in a moment. So in the early 80s and of the 70s, Bramson came and he actually managed to compute the size of this correction term. And it turned out to be quite large, and it's actually minus 3 half log t here. Okay, so what he showed is that for any MT of this form, so you take 2t minus 3 half log t plus some constant plus a small o of 1, then this happens. So you have convergence of your solution, okay, toward this shape W star. And of course, the value of the constant c here corresponds to the horizontal shift of W star. So for instance, if you want to converge to the unique traveling wave solution of speed 2, whose value at 0 is 1/2, then this determines completely the constant you have to put here, obviously. Okay? So that's one of the results. Okay, and the other very important part, of course, of Bramson results is is that you can, now you're not restricted only to those Heaviside initial conditions. He showed that in fact, this is going to hold whatever the initial condition, provided it decreases fast enough near infinity. And so what does decrease fast enough mean? So I don't want to go into detail, I'll give a hint later on. But you can think of something which is 0 after some time, so which reaches 0 in finite time. So essentially the Heaviside initial condition plus a compactly supported perturbation. Okay? All right. And okay, and then you may ask, and indeed it's interesting, okay, what happens if my initial condition is not fast decreasing? Okay. Well, it turns out that there is you can get any of those, you can converge to any of those traveling wave solutions. Okay. So if your initial condition decrease like e to the minus lambda x, okay, and lambda is smaller than 1, what's going to happen is that you're going to indeed converge to a limit shape again once you center appropriately. Okay, so now I have a new centering term here, m lambda t, and I'm going to converge to a new shape, w lambda x, and w lambda x is actually the traveling wave with speed c lambda, and c lambda is given by this expression here. Okay. So there is this very nice theory here of speed selection, which tells you that essentially it's the behavior at infinity of your initial condition which determines the speed of your front. Okay. And this is okay, I'm going to say that in a moment, but it's a very general phenomena. So when you have those reaction-diffusion front, essentially you're always going to have such a curve which relates the rate of decrease of your initial condition to the speed of the front. Okay? And okay, so the next step in this story is more recent. It's early 2000s. And it's a conjecture or prediction by physicists, by Ebert and Van Sarlos. So again, they place themselves in the situation in which your initial condition is fast decreasing. So again, think of the thing which reaches 0 in finite time or is compactly supported. And of course, I mean, once you have Bramson result, it does not really make sense of asking if you're just interested in the convergence to the traveling wave, you don't really care what you put here, right? Whatever you put here, the convergence is going to happen. Okay, so what I need to do if I want to say something about what happened here is I need to have a harder definition of front position. So not just converge to something. Okay, so there's many ways, in fact, in which you can define what is the position of a front. So maybe the most natural way is to say, okay, let me look at, so if I have decreasing initial conditions, always going to stay decreasing, so I can say, let me define m alpha of t to be the point where my solution is equal to alpha. Okay, so think of alpha equal 1/2. And if you think of this function as the 1 minus the CDF of some variable, this is just the median for this distribution. Okay, if alpha equal 1/2. Another thing you could do is still thinking about this as the 1 minus the CDF of some distribution. You could take the expectation of this distribution as your definition for the position of a front. And indeed, this is something you can do. This one is more problematic. You could, if you look at what this W star looks like, it looks like there is a unique inflection point. Of course, it doesn't need to be unique or even finite, but maybe under some good initial condition, you can prove unicity of the inflection point, and that might be a good way to measure the position of the front, but this is more problematic. Anyway, I'm going to concentrate on this definition for the position of a front, okay? Okay, And now what Ebert and Gonzalo say is that, yeah, of course, M alpha t is 2t minus 3 half log t plus c. And this is, again, Bramson expansion. So this is already contained in Bramson. And Bramson tells you, it gives you that M alpha t indeed is this plus a small o of 1. But now that you have a hard definition for the position of a front, well, you can say what happened next. And what Ebert and Gonzalo predict is that there is actually a universal expansion. I'm going to explain why universal. And they say that the next term is minus 3 over root pi over t. And then you have some smaller order term. And in fact, what they predict is an expansion in powers of 1 over root t. But let's look at this term here. So of course, this is a good way to center your solution. You're still going to converge to W star because this belongs to the Bramson expansion family. Okay. But I'm going to say why this term might be interesting and what it means. Okay. Okay. So I mentioned that this term, there was a claim of universality behind this term. So I'd better explain what I mean here. So the first thing you can observe is that in fact there is nothing really special about this plus u, 1 minus u. In fact, if I replace this, so my non-linearity here, which was u, 1 minus u, I can replace by any function which has this kind of shape. So what I mean here is that it's positive. It stays below the first diagonal. It has derivative 1 at 0. Okay? If you have this, then the exact same expansion hold. Okay? For the position of the front. So you have the same phenomena. You converge to a traveling wave. Okay? And the centering term is again going to be the exact same thing. And you're going to even have this small order correction, which is going to be the same. So C is not going to be universal. The only thing that changes here is this C constant. So those two guys are universal. This one is, but it's a term that goes to 0, and this one is not. So it's already a bit strange. More generally, for a pull front, okay, so pull front means a front where the speed of the front is decided by what happened at infinity, so it's a bit tautological, but so the front where this kind of phenomenological analysis hold, okay, you're going to have something very similar. So you're going to have, remember this function I drew earlier, which relates the rate of decrease of your initial data to the speed of the front. Okay, so you have this minimum here, which I call point gamma c, and which gives you the critical speed vc. And in that case, well, you again are going to observe the formation of a front, okay, which is going to look like the critical traveling wave if your initial data decrease fast enough, and the expansion is going to look like this. So up to a small change of the constant, you see it's in the same form than this one. So this should hold. So this kind of thing should hold in a lot of models where you have diffusion and reaction. So, okay, I'm going to talk about some of them in a moment. All right? Okay. So, so all these terms here are well understood, and this one is a new one. This is the one I want to talk about, and for now, this is not known, right? So this is a prediction. Okay. So why, as probabilist, why should we care about this? Okay. So you probably know this, but there is this important connection between the KPP equation and branching Brownian motion. So let me remind you what the branching Brownian motion is. Okay. So you have particles which are going to move according to Brownian motions, but I'm going to scale things by √2 because I want this to match with my with my equation, and my generator had a Laplacian, not half Laplacian, so I need to do that. And those particles, what they do is they split into two particles at rate 1. And then each of these particles start again the same process, and so on and so on. So if you do a picture of what this might looks like, you have your initial particle here, which is moving around as a Brownian motion. then it splits, and then each of those splits again, and so you have this growing cloud of particles, right? And so I'm going to call xi of t the position of the particles at time t, okay? And I'm going to take some function, some test function phi from the real numbers to 0, 1. And McKean representation, which is really just a Feynman-Catch representation for the FKPP equation, tells you that if you take this function, so u of x and t is the expectation. So this is the expectation for the BBM, for the branching Brownian motion. And you take the product over all particles alive at time t of phi applied to x minus xit, for instance, here. This is one way of formulating this. Well, this guy solves, okay, so it's not exactly the KPP because I have minus instead of plus here, but just by taking 1 minus u, then you recover my usual KPP equation. So this guy solves the KPP equation, okay? And the initial condition is, my initial data here is phi. So it's really remarkable, of course it's Feynman-Catch, but you can represent for any initial condition for your PDE, you can represent the solution as an expectation of a functional of branching Brownian motion, okay? And maybe the one which is very well known is what happens if you take phi to be a step function like this, okay? So this is at point 0, so it's 0 left of 0 and 1 to the left of 0. Well then, okay, what is u of x and t? You see, it's the expectation of the indicator function that all those guys are positive. Is this the right way? Yeah, I guess I did it the wrong way. It looks the wrong way? Yeah, okay. Well. So I mixed up the way. Let's see. So this has to be positive. No, it's okay. Okay, sorry, it's okay. So this is indeed the probability that they are all less than x. So this is the probability that the maximum is less than x. Okay, and so what this tells you is that the cumulative distribution function, so u of x and t, is just the cumulative distribution function of the maximal position. So you just proved that the CDF of the maximal position is actually a solution to the KPP equation, right? And and so what does, okay, so now that you realize this, okay, what does Bramson tells you? Well, tells you the following. Okay, so let me call MT this maximal position, okay? This is the rightmost particle, or the maximal one. So I've just told you that u of x and t, which is, okay, so let me take 1 minus, it doesn't change much, the CDF. Well, this guy solves the FKPP equation, okay? But, and what is the initial condition? Well, the initial condition, according to what I said, is my Heaviside initial condition, right? Because the initial condition is phi, or 1 minus phi in this case. And so what that means is that if I center by MT, and MT is anything like that, and I can put any plus small of 1 here, I don't care. I can take this without it. I center around MT, and then I know that this guy converges to W star. But this is, of course, just the CDF of capital M, the maximal minus M. Okay? And therefore, you've just proved for free that the random variable capital M minus small m, so the position of the rightmost centered by this guy, converge in distribution. It's tight and converge to a distribution W. And not only that, but suddenly this limit variable W, you see that its cumulative distribution function is given by this critical traveling wave. All right? So this tells you that those traveling wave and those solutions to the FKPP equation are really important if you want to study what happened near the extrema of the branching Brownian motion. Okay. Okay, so now let's go to what we did in this work. Right, so what I'm going to do is I'm going to change a little bit the problem. Okay, because so we wanted to understand this Ebert and Van Sarlo's next order term, but it's very difficult to do it on the actual KPP equation, so we're going to take a problem which turns out to be a bit simpler to analyze. So what we do is we linearize the problem. Okay, so I'm going to cut away, I'm going to get rid of this u square minus u square term, okay? So if you do that, okay, the equation is dtu minus Laplacian u plus u. So this is now just the heat equation plus a growth term. And of course you have unbounded growth, right? So, so if you do that and you look at the solution, then u of x and t is just the expected density of particle near position x at time t if you start from one particle at 0. Okay, so if you hope to get something that looks like a traveling wave, it's not good. Okay, so you need a saturation mechanism. And the way you do that here is that I'm going to introduce a killing boundary empty. Okay? So my problem now, I have also this boundary which is unknown, and in some sense it's a bit like in a free boundary problem. I want to solve something like that, but I don't know what empty is. Okay, so if I just give you this, of course this is not well posed. I mean, for any empty I give you, I'm going to be able to exhibit a solution. So I need to ask something more if I want to have a meaningful solution to this problem. Okay, so what more can you ask? Well, the idea here is I want to impose that, okay, what I'd like really to happen is that seen from empty, that empty is a centering term, and that to the right of this killing boundary, I see a limit shape arise. Okay? This is not the only thing you can ask, of course, in this problem. I mean, you can impose some other condition. For instance, you can ask, okay, can I find solution to this two equation, and also maybe, I don't know, that the solution at distance 1 from this killing boundary is always exactly 1. Okay, or maybe the derivative at the killing boundary is exactly 1 always. Or maybe, and this one I'm going to come back to this one because it's very interesting, you want that the total mass to the right of the killing boundary is exactly 1 at all time. Okay, you want a probability density. So this is what I'm going to call a hard constraint, and this is a soft constraint, and you're going to see why in a minute. So maybe, what do I want to say? Okay. So maybe before I move on, one thing I can say is okay, we can think a little bit about what's going to happen. Okay, so if you start with your killing boundary at 0 and you have an initial data which is something like that, and you don't move your killing boundary. Okay, so you fix this point and you say the solution at this point at 0 always has to be 0, but this point doesn't move, and you let it evolve according to this equation. Then the growth is going to make it grow without constraint, right? So you're not going to get convergence to such a phi. On the other hand, if you take the same kind of initial condition, but now the point where you kill, where the solution has to be 0, is moving to the right very fast, okay? You see that you're going to eat up a lot of the mass. And if you move fast enough to the right, then the solution is going to tend to 0, right? So this tells you that there's some sort of equilibrium speed right here, where if you move just right, then indeed you might get this limit shape, right? Okay, so maybe it's time to give a result. Okay, so suppose that so h of x here, I'm sorry, this is a change of notation, but h of x is going to be my initial condition. So this is this initial shape here with which I start, okay? And what I ask is that it decreases fast enough. Okay, so what is fast enough here? Well, I want it to decrease at least as fast as x to the minus 2 times e to the minus x. Okay? So that's already in Bramson, and essentially this is, okay, so if you are on the whole real line, this is what you need so that your expansion look like 2t minus 3 half log t. So I'm going to introduce RT here, which is the rest. It's just this is just some way of writing RT here, and MT here now is not the same thing as before. It's not the place where my front is 1/2 or whatever. This is the position of my killing boundary. Okay, it's a bit different. Okay, so here is the first result. So if RT goes to 0, meaning if you choose empty exactly like one of those Bramson terms, okay, then you have convergence. And not only that, but the limit is alpha time is proportional to x times e to the minus x. Okay? So you know there is only one shape possible for the limit, and there is kind of a scale factor which depends on what? Well, it depends on this A guy here, which is here, and a bunch of other stuff which are related to the initial data. Okay, so which depend only on h. So I don't want to go into that too much for now. If I have time, I explain a little bit more. But I know I can compute this alpha anyway. Okay, and that's not all. So if you have only this, essentially what you do is you just recover Bramson for the linearized version of KPP. So that's interesting, but it's not really the goal here. So okay, so I need to do a further hypothesis. I'm going to come back to it. So I suppose that not only r goes to 0, but I have to suppose that r dash dash, the second derivative of r, is also converging to 0 fast enough. And fast enough means here faster than t to the minus 2. So if you believe, for instance, that Ebert and Van Sarlos are right, and that this is 1 over root t, indeed, this is going to be, and that there's and that the further terms have smaller second derivatives, then you're going to get here t to the minus 2.5 for r dash dash, plus smaller order terms. So what happens if you can suppose this? I'm going to try to explain also the meaning of this hypothesis later. Well, you can say something about the speed of convergence in that case. Okay, so remember that if you have this, then this guy, okay, the solution centered by M, converge to alpha x e to the minus x. So this is this term, this one here, times this. And all those other terms here are error terms. Okay? Okay, so the first one is RT, then you have this 3 root pi over root t, which is exactly Bertrand and Sarlos, right? And then you have all those big O's here. So let's see what this means. Well, if you want this error to be as small as possible, okay? It's not hard to see that, for instance, this one is log t over t. If nu is less than minus 2, you see that this is also going to be small. So you might need to ask that nu is, for instance, smaller than even minus 3 or minus 4, but okay, let me do that maybe later. And so on and so on. This is also smaller order than 1 over root t. So you see that this is going to be the biggest term. So if you want to cancel this term, what you need to do is you need to choose RT to be minus 3 root pi over root t plus smaller order terms. Okay? And if you do that, well, you kill this term and you just have the rest here. So the upshot here is that choosing RT exactly as Ebert and Van Sarlos predicts is the choice which yields the fastest convergence. Okay? Okay, so another way to say that again is that, okay, so if you choose RT without paying too much attention, essentially the speed of convergence is going to be like 1 over root t. Okay? But if you choose RT exactly as Ebert and Van Sarlos predict, and nu is small enough, then the speed of convergence is actually like log t over t. Okay? So we conjecture that this is also true for the KPP equation. Well, we conjecture this is also in the prediction, of course, of Ebert and Van Sarlos, meaning that if you center by a MT, which is any Bramson MT, essentially you're not centering right, and so it means that you're making an error in your centering, which is of order 1 over root t, and so the difference between the centered U and the critical traveling wave W star is going to be of order 1 over root t, whereas if you center just right, again, I think that the speed of convergence, okay, of the KPP solution around its median, for instance, to the critical traveling wave is going to be of this order, which is also an interesting result, of course. Okay, so why is this interesting? Okay, again. So, okay, so now I'm going to speak about a slightly different question, which is still open, but I think is really interesting and is related, of course. Okay, so if you take a model of NBBM, so NBBM, so it's a branching Brownian motion with selection, which works like this. So you start with n particles, okay, and each particles move around on the real line like a Brownian motion, and they all branch at rate 1. So this is, so far, it's just a branching Brownian motion. The difference now is that each time I have a branching event, I want to keep my population size constant to capital N, so I kill the leftmost particle. Right? If it's the leftmost particle which is trying to branch, you just erase the event. And so what you have is a cloud of capital N particles which is moving to the right at some speed. So this is something, for instance, that Pascal has studied a lot. So I'm going to call mu and t the empirical measure of this particle system. I give a mass 1/n to each particle. And I'm going to call ln of t the position of the leftmost particle here. Okay? So this is now mostly open, but it's related to something we know, so I'm going to tell you exactly. So what should happen here is that if you look at jointly at ln t and this empirical mass measure, this is going to converge to the solution of the free boundary problem I've already introduced earlier, which is, okay, so you have your favorite heat equation plus growth, right of Lt. The u of Lt and t is 0 at all time. And because now you have an empirical probability measure, the integral from Lt to infinity of your solution is 1. So it's one of these hard constraints I mentioned earlier. Okay? So what I claim is that on a finite time horizon, at least, the solution of this system of PDE should be the hydrodynamic limit of this particle system. What we believe to be the case is that for the solution of this system, at least Lt should behave exactly as predicted by Ebert and Mansarlos up to the full expansion. So this is not done, but Duret and Reminick proved the hydrodynamic limit. So they did not prove this, but they proved the hydrodynamic limit for a very closely related model of a branching random walk instead of branching Brownian motion with selection. Okay, okay. So this is another motivation for being able to look at these further corrections of this position of fronts and killing boundaries. All right. Okay. So if I sum up what I've said so far, and I try also I need to mention a couple of results which are known by now. Okay. So first, for the real full FKPP equation. So the one with no killing boundary on the real line, if you start with a fast decreasing initial condition, okay, and you define the position of the front as the alpha quantile, so the first time your solution is alpha, then what Ebert and Mansarlos predict is that you have an expansion like this with gamma of alpha, which is universal and does not depend on alpha. Okay, so there has been in the past few months, so actually in December, there was a work in PDEs by Nolan, Rockjoffre, and Rujic, where they claimed that they had proved this with a gamma of alpha which depended on alpha. So this is exactly the opposite of everything I've been telling you so far. So that made us slightly nervous. But turns out that we went in and if this were to be true, it has some pretty strange consequences. And in fact, they've now changed their claim, and it appears that the gamma of alpha is actually going to be minus 3 root pi, exactly as predicted by Ebert and Mansarlos. So all is well on this front. But it's not, for now, it's not done yet, at least. I believe that there are techniques which are essentially techniques called the matching of asymptotics in PDEs, is going indeed to be able, they're going to be able to do this. I have no doubt about it. So the next thing I mentioned was a related problem where you have a free boundary problem, okay, where you kill at some position LT, and you need some extra condition, okay, and so if you just want a soft condition where you just impose that seen from LT you converge to something, then what we proved is that the Van Sarlos correction, so Ebert and Van Sarlos correction, gives the fastest convergence. If you want some hard condition, like this one, which is related to the NBBM, then this is pretty much open. In fact, even, so I had a discussion with Pascal earlier this week, even proving existence, well, you can do it by this kind of heterodynamic limit, in fact, but if you want to do it by usual PDE argument, it's not that straightforward. And all the tools you're used to, like the comparison principle, the maximum principle, and so on, becomes a bit harder, and you have to be very careful here. So unicity, for instance, is not at all obvious. Okay, so maybe I want to give you a little bit of an idea of how you go about proving this result. Okay, how is it that you can actually get such detail on the rate of convergence and the error you're making in the convergence here. So, again, it's pretty classical, and what we're going to do is we are going again to push the techniques of Bessel and Brownian representation for the solution of these equations. Okay, so the key idea is the following. Okay, so what I'm going to do is I'm going to use the fact that U is really the solution of a linear equation. So what that means is that I can really write this solution as the integral of my initial condition against a solution where this is a solution started from just a mass at point Y. Okay? And then I just sum them up against H, and this gives me my full solution. So what is this Q guy actually? Okay, so Q of T, X, and Y is a solution of my heat equation plus growth, where I have a killing boundary at MT, and my initial condition is I have a Dirac mass at point Y. Okay? And I let this evolve, and I see what happens. So what is the solution? Okay, so what is this? What is the solution of this equation with this initial condition? Well, I mean, it's just a heat equation plus Q, right? So this plus Q here is going to give me an exponential growth in my solution. Okay, so I put this in front. But once if I didn't have this here, this would just be the density of a Brownian motion. Okay, so the density of a Brownian motion killed at MT started from Y around point X. Okay, that's all what it is. So this is just exponential time t times the probability starting from Y that my Brownian motion is at time t is at this near position X and has always been above this killing boundary. That's all what it is. And okay, so now instead of looking at, remember that I want to look at U of X plus MT, not U of X MT. So let me look at Q of T, X plus MT and Y. Okay. So then I just have, I will just have this expression here, and I will just have BT minus MT here in dx. But instead of that, what I can do is I can do a Gersonov transformation, so I force my Brownian motion to have a drift M. So what I want is that BT minus MT is a Brownian motion. Okay, and if I do that, well, this becomes just, okay, once you do this, okay, so now you want BT minus MT to be in dx, but now BT minus MT is my new Brownian motion, so BT in dx, and you've always been above 0 now, because I've taken out this drift M. And this stuff here is just the Gersonov term. Okay. Right, so first this green expression here, well, that's just the transition of a Bessel process, right? It's a Brownian motion conditioned to stay positive. So this, I know what it is. So it gives me this term. Okay? You can read it in books. So what about this one? Well, okay, so this is a Gersonov term. So what is a Gersonov term? Well, it's going to involve integral of M prime against dB and m dash dash, and so on. What you get in the end is you get those, okay, and you do an integration by part, but, okay, so the ET is this one. This is part of my Gersonov transform. This is also in my Gersonov transform. And then the CT of y and x contains all the random parts. And what it is exponential of 1/2 integral of m dash dash against a certain process. And this process is what? Well, okay, so you see here, this is a Gersonov transform, but conditionally on the fact that I end up at position x and that I'm always positive. So this is another word, it's my Gersonov transform for a process which is a bridge, a Bessel bridge from y to x. Okay? So now what I need to do is I need to be able to compute this kind of expectation, okay? And you see that, okay, so this is a special way of writing this expression. I take my Bessel bridge and I subtract the line from y to x. Okay, it's going to be useful further down the line. Okay, so again now I'm interested in computing this kind of expression, right? And yt of x and y is this complicated integral here. Okay, so let's think about what happens when t becomes large. So when t becomes large, this process, this Bessel bridge, minus its, so you see it's the difference between this pink curve here and this green line here. Well, it looks more and more like simply a Bessel process started at position y minus y. Okay, so when, at least on a compact space near zero, in a compact interval near zero, it's clear. T is going to infinity, so the slope is getting smaller and smaller. You're not seeing where you're going to end up. You're still conditioned to be positive, and you're still subtracting the line. So in the limit, this stuff converges pointwise to a Bessel process started from y minus y. Okay, and so let me call I of y this, so this is 1/2 of the same integral, m dash dash s, against this limit process, okay? And what you can guess, I think, is that with good condition on m, then the limit of this term is going to be exactly expectation of the exponential of this limit integral, okay? So there's a little bit of work, but it's really doable. And in fact, you can do better here. What you can show is that this term psi t of yx is uniformly bounded between two constants, and also the dependence on x does not really matter. So you can replace psi t of yx by psi t of y0, and you have a very good control over the mistake you're making when you do that. So okay, so essentially. This delta and this psi infinity thing, which appeared in my expression for this alpha constant earlier, well, are here, but okay. Okay, so okay, that's another important part, is that if you now, okay, so now you fix x to be 0 and you look at psi infinity, so the limit of psi t y, and you take again now a limit in y, and you have again a limit for this, which you call E delta, and delta is just this. Okay. So let's see how you use this. So you're going to write that I'm going to want to use, okay, I'm not going to get the Hilbert-Van-Sarlos because this will take too much time, but I'm going at least to convince you that you get the Bramson expansion. So, okay, so I'm going to write my Killing binary as Vs plus some smaller term, okay? And I'm going to say that delta S is big O of log S. So this is exactly equivalent to my hypothesis actually on the second derivative of R that I had. And remember that the last thing I wrote was this line, right? So you have this expression for Q of nt plus x and y. So this now, with this new notation, I can rewrite in this way. Okay, so I replace the psi t of yx by psi infinity of y0, which is the limit of psi infinity of y0, and then I introduce all these small errors I'm making, which are all absorbed actually in this term, which is the big O of log t over t. And so now this is written like that. Okay, so why is this good? Okay, well, okay, it means that my whole solution, again, remember, it's the integral of this guy against h, right? So it's going to be those terms, which are not dependent on y, times some capital H term, which is the integral which contains my initial condition h of y here, okay? So I'm not going to tell you exactly how, but okay. So the game here now is I want to pick v and delta. Okay, so that's my m killing boundary, so that I get a non-trivial limit for this, right? So how do you do this? Well, the first thing you notice is that if h is indeed fast decreasing, is decreasing fast enough, then this h here has to be bounded. So you can basically say that this guy here is a constant. And once you have this, well, you see that first thing is you need to kill this exponential growth here. So that means that you need to choose v equal 2, because otherwise you have a e to the t to something, so either positive or negative, but clearly then you cannot have a non-trivial limit or an explosive limit. So you need to choose v equal 2, that's the first thing. And now what you're left with is, okay, you have this t to the minus 3/2 that goes to 0, and the only thing that can compensate this t to the minus 3/2 is this v over 2 delta t. Okay? And if you want to compensate t to the minus 3/2 by v delta t, where v is 2, it means that you have to choose delta t is minus 3/2 log t. Okay? So that's how you recover Bramson term. Okay, so there's a more painful slide, which I'm not going to talk really about, but which tells you that in fact you can play this game with any decrease for the initial condition. Okay, and then you look at what happened to your integral, and you look at what are the y which dominate this integral against the initial condition, and this tells you what is the centering term and what is the limit shape, the traveling wave, in fact. Okay, and I'm going to stop here. Thanks.
Do your results generalize to higher spatial dimensions?
No, I don't think they do. I mean, it's an interesting problem actually. So what will be the analog of this kind of free boundary problem in higher dimension? So maybe you could have kind of a growing ball where you kill things, but actually I'm not. No, I don't. We have not thought about it. So maybe, but I think you have some considerable difficulties to overcome to do that.
Yes, so your study concerns the case when the initial condition decays exponentially fast. Yeah. And I was wondering what is known in the case when the decay is much smaller, like polynomial decay.
Okay, so it's partly here. So if you have, so first of all, you can ask what happens when you have a slower, you still have an exponential decay, but at a rate which is smaller than 1, right? So like e to the minus x over 2 or something like that. So in that case, what you're doing is you're changing the speed of the first order here. Okay. And you're changing, of course, the shape of the limit. But if you have something which is decays like polynomially, I'm not sure what do you have. Do you jump immediately to 1 or?
I don't know, but I think so. You can still make sense of the median 1/2,
yeah,
which will give you a certain behavior,
yeah,
but also the median of of 1/4, and this will have a different behavior. And
so I guess you have at least an accelerating behavior, right?
Well, I was thinking that what you will see is basically the rising of the front going up like this.
Yeah, but if you look at M alpha, it's going to move faster and faster, I think, to the right. That's actually very...
But
I don't know what's known.
No, I thought there might be interesting behavior to be...
actually, probably, yes, you're right. I'm not sure what's known in this direction, but...
Is there a question? So, thanks a lot.